Today we are looking at graphs, an important data structure in the computer scientist arsenal. Graphs are important because they can be used to represent essentially any relationship between entities, like a rail network representing cities connected to other cities by a direct line. During the video, we'll be covering some definition and describe different types of graphs. Finally, we will be looking at how to represent them from a computer science point of view. First, let's define what a graph is. A graph G consists of a set of vertices V together with a set of edges E. An edge connects two vertices together. An edge represents some form of relationship between two vertices. An empty graph is a graph where the set of vertices V is empty, and therefore the set of edges E is also empty. Notice that a vertex may not belong to any edges as shown by vertex K. For example, K could represent a city on an island that is not connected to any other cities on the mainland via a railroad. Graphs have many properties, and we will express them when and where they are needed. In this video, we need to define three properties related to the number of edges in a graph. A graph is said to be dense when the number of its edges is close to the maximal number of edges, that is, of the order of the number of its vertices to the square. On the opposite spectrum, a sparse graph has few edges relative to its number of vertices, usually of the order of the number of its vertices. A complete graph is a graph in which each pair of the vertices is joined by an edge. A complete graph contains all possible edges, and therefore is a dense graph. On the left-hand side, you can see an example of a complete graph composed of 6 vertices. There are many types of graphs, and it's very important to be able to recognize them, in particular, when you want to use an algorithm to solve a problem. You may need a different algorithm to solve the same problem depending on the type of graph. The first type of graph is an undirected graph. An undirected graph is a graph in which the edges have no orientation or direction. That is, the edge UV is identical to the edge VU. It means that if a node U is in a relation with node V, V is also in a relation with node U. It is the simplest type of graph. An example of such graph is a social network. Nodes are people, and edges represent bidirectional relationship between people, like being friends. Study of social networks found application in many disciplines, such as sociology, economics, biology, and counterterrorism. In contrast, a directed graph, also known as a D-graph, is a graph in which edges have orientation. In this case, edges are represented by an arrow. When considering edge from U to V, I will use the term source, origin, or tail to refer to the node U, and target, destination, or head to refer to the node V. Note that if a D-graph has an edge UV, the edge VU may or may not exist. An example of such graph is a graph representing followers in a social network, such as Twitter. I may follow a person, such as a famous actor, however, it is unlikely that this celebrity follows me back. This means that the relationship following is directed. Study of such graphs can be used to determine influencers within a group of people. Another example is the structure of a website containing many pages. Each page is considered a vertex, and an edge exists between two vertices if the source page has a link to the other target page. So far we have seen unweighted graph. That is, the edges have no associated weight. A weighted graph is a graph in which edges contain a certain weight. The weight represents arbitrary values such as distance, cost, quantity, flow, and so on. For example, The graph shown could represent cities connected by railroad, on the weight as the distance between the cities. A weighted graph can be directed or undirected. Edges in a weighted graph can be denoted as a triplet U, V, W, where U is the source, V is the target, and W the associated weight. Examples of such graphs are flow networks, where edges are pipes and nodes are intersections between pipes. Flow networks are also used for transportation problems, such as maximum traffic through roads, or analysis of bottleneck in production factory with various workshops and tools. Usually, weights are strictly positive. However, in some cases, they might be negative. A negative weight could represent the energy used to go from state A to B, whereas a positive weight represents the energy produced to go from state B to A. In some graph, the weight for the edge UV may differ from the weight of edge VU. This is the case for the edge between node B and C. This could represent a road having 4 lanes going from B to C and only 3 from C to B. This would allow more vehicles going from B to C in a given unit of time, hence a higher weight. Now that we understand what a graph is, we need to address the issue of representing a graph on a computer. That is, what data structure should be used to implement a graph. Careful consideration should be taken as the choice of data structure can have a huge impact on the performance of some algorithm, as well as the readability of your code. The simplest representation is an edge list, or an array of edges. For a weighted graph, it is a list of triplets U, V, W, containing the source U, the destination V, and the weight W of an edge. In our example, the edge from A to D is represented by the triplet A, D, and 1. The main issue of this representation is the lack of structure. For example, to find the list of all nodes in a graph, we must traverse the entire list. Furthermore, what about nodes that are not connected to any other nodes? A solution to this problem is to have 2 lists, one for the edges and one for the nodes. The edge list of an unweighted graph contains pairs UV, where U and V are the nodes connected by an edge. In this case, the edges AD and DA are both represented by the pair AD. This graph implementation is rarely used due to its lack of structure. Another simple way to represent a graph is an adjacency matrix. The cell MUV, also noted M square bracket U square bracket V, represents the edge weight of going from node U to node V. The rows are the source node, and the columns are the target node. For example, the weight 8 of the edge BC is stored in the cell at the intersection of the second row and third column. You may have noticed that so far I did not put a value in the cells when the corresponding edge does not exist. There are several conventions to represent the absence of an edge in an adjacency matrix. When no edge exists between node U and V, MUV is equal to plus or minus infinity or equal to 0. The choice between the 3 values depends on the type of problem we try to solve. It is usual to use a negative infinity for a maximization problem, and the positive infinity for a minimalization problem. When considering unweighted graph, the adjacency matrix contains only zeros and 1. MUV is equal to 1 if there is an edge going from node U to node V, and MUV is equal to 0 otherwise. In the case of an undirected graph, the matrix M is symmetric, that is, MUV is equal to MVU. A better alternative to the edge list is the adjacency list. An adjacency list represents a graph as a map from nodes to their list of edges. In this representation, a node only keeps track of its outgoing edges. An outgoing edge of node U is an edge where U is a source. In the case of node C, we only have to track the outgoing edges C towards B with the value 6, and C toward D with a weight of 3. Note that the node B does not have any outgoing edges, and therefore the node B is mapped to an empty list. As I said earlier, it is important to understand the different data structures used to represent a graph, and especially knowing which data structure will be more suitable for your problem. To this end, we'll be comparing each data structure against 3 dimensions. The first one, the space needed to store the graph. The second one, how efficient is it to find the weight of an edge or to see if that edge exists. And finally, iterating over all edges of a graph, a task that many algorithms need to perform. When considering the space used to store a graph, the edge list and the adjacency list perform better on sparse graph. For example, a graph of a 1,000 node requires a matrix of 1,000,000 cells. On the other hand, if on average each node has a degree of 10, that is, the node has around 10 incoming and outgoing edges, we need to store only 5,000 pairs of value. Less than 1% of the matrix is used to store useful information. The remaining 99% is just a waste of space. However, if the graph is dense, then the number of edges is of the order of 1,000,000, and storing 1,000,000 pairs of value in a list becomes far less efficient than a matrix. To find the weight of an edge, adjacency matrices are extremely performant. We say it is in constant time, which means, in layman terms, that it is almost instantaneous to retrieve the value of whatever the size of the graph. On the other hand, using adjacency list or edge list means that we need to traverse the list until we find the edge of interest, before being able to return the weight of the edge. We say it is linear with respect to the number of edges, E. In other words, in the worst possible cases, the edge is the last one of the list, and we have to look at all the edges before finding the one of interest. The more edges on the graph, the less performant is the lookup operation. Finally, iterating over all edges is more efficient using edge list or adjacency list. It is particularly true for sparse graph. Again, considering a graph of 1,000 nodes containing around 5,000 edges, it will require to visit all 1,000,000 cells of the adjacency matrix. The difference in performance is less of an issue for dense graph. Now that we have a good idea of what graphs are and how to represent them, we will be able to explore some of the many problems that can be solved using graphs.